I coded these AI to learn how to play Minecraft. They learn using reinforcement learning, essentially trial and error to train their neural networks to control the player and hopefully survive against the zombies. Let's break this down. I'm using a technique called Neuro-evolution, which combines both neural networks and an evolutionary algorithm. In this case, the genetic algorithm. Both are real classics in the world of machine learning, and commonly used in videos about making AI play games. But for the sake of completeness, here's how it works. I have 20 bots, each with their own randomly connected neural network. I let them loose in a big arena with a bunch of zombies and see how well they survive. They lose 10 points every time they get hurt, and 100 points when they die. And they gain 20 points if they punch a zombie. Usually when people do this sort of thing, they make death an instant game over for the AI. But in this case, I'm letting them respawn at a random position inside the arena, and just keeping track to see if they die more. After a minute of collecting data, we can start the learning process. The idea with the genetic algorithm is that instead of improving the individual AIs, we're trying to improve the population as a whole. To do that, we're adding all the scores together and dividing by the number of bots to get an average score. Any of the AIs that scored less than the average get deleted. Or to be specific, the neural networks get deleted to save time having the bots log into the Minecraft server. They are then replaced by a bunch of new neural networks. We could make these randomly like we did at the start, but a better idea would be to make a copy of an existing neural network and mutate it a little bit by adding a random change to it. The idea is that since these neural networks scored at or above average, a slightly modified version of them might be more likely to perform well than one that's completely random. It's entirely possible for the random mutation we've made to either make the model better or worse, so we'll need to do further testing to know for sure. Another way of creating neural networks that we can also try is to take two existing networks and combine pieces of each of them. To make this more biased towards ones that scored better, I'm selecting 3 at random, and of those 3, I'm combining the 2 with the highest scores. We're now on what we'll call the second generation of AIs, and we'll need to test them the same way we did the first. Each one starts with a score of 0, and I'm running this command to scatter them randomly around the testing area. I'm also giving them regeneration with a huge multiplier for 1 second to bring their health back to full. Since, as I mentioned earlier, I'm reusing the same bots from before with a different neural network. Once it's been another minute, we'll have enough data to repeat the steps we took earlier and create a third generation. A minute after that, we can make the 4th generation. So on and so forth, gradually improving every time. Of course, I don't do any of this manually since I've written code to automate all of it. So while they're cooking, let's talk a little bit more about how they work. As I mentioned earlier, the main algorithm controlling the bots is what's called a neural network. The way I think of a neural network is as some code that transforms vectors from one space to another, based on the patterns it learns during training. If you're unfamiliar with vectors, you can think of them as a list of numbers. In our case, we have an input vector with some information about the world, and we want it to somehow be converted into an output vector that tells the bot how to move. For now, we'll keep things as simple as possible and say that our input and output are both single numbers. I don't know what these numbers would represent, but that's fine because neither would the neural network and it's just an imaginary example. We can put these numbers on a graph that shows the ideal output for a bunch of inputs. The relationship between these numbers could look like anything, but we're trying to keep things simple for ourselves, so let's say it happens to be a straight line, aka linear. And since it's a straight line, we can represent the relationship between the numbers with a really simple function. Output equals input times a number plus another number. The number we're multiplying by is called the weight, and the number we're adding is called the bias. The specific numbers we're adding and multiplying would change depending on the relationship between the input and output. And since we're using a genetic algorithm, we're trying out a bunch of random combinations and seeing which ones work better. Then every generation, it's like we're making a bunch of new guesses near the best guesses from last time and slowly honing in on the optimal solution. Except we don't know what the actual optimal solution is, or if one exists at all. Instead, we're just trying to maximize a score by not getting eaten. Going from our little toy example to actual neural networks might seem difficult, but it's important to remember that the complexity of these systems is an emergent property. It comes from combining a lot of simple elements together. We'll do it in 3 steps. The first step is to make both our input and output into vectors. The bias also becomes a vector, but the weight becomes a matrix. A matrix is like a vector, except it's 2D with both rows and columns. This also allows our output vector to be a different size to our input vector, but that's not important right now. If you need help with this part, you can search for tutorials about adding vectors or multiplying a vector by a matrix. The second step is to add layers in order for our neural network to learn more complicated patterns that aren't just a straight line. And by that I mean, instead of converting directly from our input to the output, we first convert to an intermediate vector and then to the output. These intermediate steps are called layers, and the more layers we add to the neural network, the more complicated the patterns it's able to learn. This also increases the necessary computing power required to make it learn anything, so ideally we'd keep our network as small as we can get away with. Okay, so there's one step left which solves a massive issue we currently have that I haven't mentioned. If you combine a linear function with another linear function, your result is still linear. Which essentially means it's the same as doing a single, different linear function. If we want our neural network to be able to model non-linear relationships between numbers, we need to introduce some curves. Which is why the third step is applying activation functions. An activation function is a function that takes in a number, outputs another number, and the relationship between the two isn't a straight line, aka non-linear. There are a lot of different activation functions to choose from, but some will work better than others depending on the scenario. A very simple one would be something like this, but the specific one I'm currently using looks like this. It's used on every value in the vectors of our layers between the input and output before we do the whole add and multiply thing. And that's it. We're done building a neural network. There's plenty more that could be said about these things, but let's leave it at that and check back with our AIs. Okay. I guess we should leave them to train for a bit longer. While we wait, you may have wondered what data I'm giving the AI in the input vector. I could be giving it information about the positions of all the blocks and entities, but that sort of feels like cheating. Another option would be using actual rendered images from the game, which is what some projects do, and of course it's how we as players see the game. This would probably be the most interesting approach in my opinion, but it would require more computing resources and more work. I've tried both of these in the past among others, but the solution I went for this time is kind of a combination of both. We send out a bunch of rays in the direction the bot is looking and measure the distance they each travel before hitting a block or entity. We can then feed this data into the neural network to allow it to see distance. I'm also scaling the distance between 0 and 1 to hopefully make it a little easier for the neural network to learn. But seeing how far away things are isn't enough, because we also need to know what things are. So each ray also returns the name of the thing it hit. The neural network wouldn't really understand a name, so we need some other way of representing it. To do that, I'm using embeddings. They're vectors that represent a specific thing in the game, and have values that help inform the neural network about that thing. Each type of block and entity get their own embedding, so there's one for zombies, one for red wool, one for snow. The values in this vector don't come from anywhere specific, but are learned during training like the parameters of the neural network. Meaning they start off random and gradually adjust until they're something useful. and because of this, we won't necessarily know what the values in the embedding vectors represent. Just that it's probably something useful for the neural network to know about the thing that it's looking at. Once we have all of this data from our arrays, we can combine it into one big vector and use that as the input. The size of this input vector will be the amount of rays we have times the amount of data we get from each ray. If the size of our embedding vectors is 3 and we have 8 rays, our input vector will end up having 32 elements. Keeping in mind that each ray also gives us the distance information. This vector is passed through the neural network and we get the output, which is used to control the bot. I'm not entirely sure what the best way to format the controls is, but here's what I've come up with. The first 2 values in the output control turning. One means turn left and the other means turn right. I use the difference between these two to determine the turn speed. The next output value controls whether or not the bot should walk forwards. If this is close to 0, the bot won't walk, and if it's close to 1, it will. And finally there's an output for punching, which only works if the bot is directly looking at an entity. I was thinking about also adding the ability to use items, but that's a little bit more complicated, so maybe next time. And after all of this, here's the bots. They've made a lot of progress, but I still have a long way to go before they'll be able to beat the game. I'll probably make some videos in the future going over more modern techniques like using policy gradients or the attention mechanism, and seeing if we can get them to play survival or something. On that note, I'll see you guys in a few weeks with my next video. Feel free to leave your ideas, suggestions, feedback or whatever in a comment. Consider giving this video a like and subscribe if you haven't already.